let's dive right in. There's a quiet revolution happening on factory floors all over the world, and it's not just about building things faster, it's about building them with materials that were basically science fiction until recently. We're talking about smart composites and the AI brains that are finally unlocking what they can really do.
So first off, why all the hype? Let's just put this into perspective. You've got steel over here, strong, reliable, the backbone of the entire industrial age. And then you have carbon fiber composites, and the difference is just staggering. We're talking 3 to 5 times lighter than steel, but with the same or often even greater strength. This isn't just a small step up, it's a total game changer for engineering.
So, that leads us to the big question, right? If this stuff is so amazing, why aren't our cars, our bridges, our buildings all made from it? What's been holding this composite revolution back? Well, the answer, it turns out, is a hidden flaw. Not in the material itself, but in how we've been trying to make things with it.
And that flaw, it becomes a massive problem when you try to go big. I mean, think about something enormous, like a modern wind turbine blade. You need that thing to be absolutely perfect, flawlessly strong from one end to the other. But creating these huge, perfect parts has always been a huge challenge because of this invisible problem that happens deep inside the material while it's being made.
That problem is called non-uniform curing. Here's what that means. When you're hardening or curing the resin that holds the fibers together, you run into trouble. See, large parts have thick sections and thin sections, and they all heat up at different speeds. The result? Some parts harden way faster than others, creating this internal tug-of-war that builds up invisible stresses and weaknesses before the part is even finished.
And the consequences of this are, well, they're pretty severe. We're talking about microscopic voids, or layers that start to peel apart. That's called delamination. All of this dramatically increases the risk of a catastrophic failure out in the real world. And that means costly, unexpected repairs and really dangerous downtime.
So, how do you start to fix this? Well, the first part of the solution was to bring in the robots. To build a perfect part, you have to lay down your material with perfect precision. And that's where a technology called automated fiber placement, or AFP, comes into the picture. It tackles the first half of the problem, the construction.
And you can see it right here in action. This robotic arm moves with just incredible accuracy, placing these ribbons of composite material onto a mold. This lets you create insanely complex shapes with a level of precision a human could never, ever replicate. It makes sure every single fiber is exactly where it needs to be.
The process itself is actually pretty elegant. The machine feeds these narrow bands of carbon fiber that are already soaked in resin. They're called tows. Then, a head on the robot arm heats up the resin just enough to make it sticky, and a roller immediately presses it down, compacting it onto the surface. This ensures you get a super strong bond with 0 air gaps. Let's zoom in on those toes for a second. You can see each one is actually a bundle of thousands of tiny, ridiculously strong carbon fibers, all pre-infused with a special resin. These high-tech ribbons are literally the building blocks of these advanced structures, laid down one after another to build up the final part.
Okay, but remember, even if you place every single fiber perfectly, you still have to cure the thing. That hidden flaw, the non-uniform curing, was still the biggest hurdle. So solving that meant going beyond just physical robots and stepping into the world of artificial intelligence, specifically by creating something called a digital twin.
So what on earth is a digital twin? Well, think of it like this. It's like giving the factory its very own crystal ball. Engineers create a perfect virtual copy of the entire manufacturing process. And this digital copy is so accurate that it can simulate and predict exactly what's going to happen in the real world under any condition you can think of.
Now, this diagram looks complex, I know, but the idea is actually pretty simple. Over on the left, you've got the real-world factory with its heaters. On the right, that's the AI, the digital twin. It pulls in data from the real world, runs millions of simulations, and predicts exactly how the part is going to cure. Then it uses an optimizer to figure out the perfect temperature settings for every single zone in real time to guarantee a flawless, uniform cure.
So, just how good is this crystal ball? Turns out it's incredibly good. Research shows this AI model can predict how the resin will actually behave with 96.7% accuracy. This is not guesswork anymore, it's precision science. It completely eliminates all the trial and error that made composite manufacturing so difficult for decades.
And here's why that accuracy is such a big deal. The digital twin doesn't just make better parts, it makes them faster. By finding that perfect heating strategy, it actually cut the total curing time by 12.5%, while at the same time improving the final quality. That is a huge win for productivity.
So, with robotic precision and an AI-powered crystal ball, we finally have the tools. But how do you take this amazing breakthrough from a single, perfect prototype and scale it up so you can have a factory pumping these out reliably? Well, there's a clear, structured path that manufacturers follow. It all starts with refining that prototype until the design is locked in. Then you move to detailed process planning, picking the right materials, designing the right tools. After that, you do small pilot production runs to work out any last-minute kinks. And finally, you roll out comprehensive quality control to make sure every single part that leaves the factory meets that exact same standard of perfection. So what's the big takeaway here? By finally solving this manufacturing puzzle, AI is unleashing the true potential of composites. And this isn't just some abstract industrial thing, it's having a real impact on the world all around us, making our machines stronger, lighter, and way more efficient.
Take the marine industry, for example. Lighter and stronger components mean ships and boats are way more fuel efficient and powerful. We're talking everything from tugboats to high-speed craft getting a major performance boost.
Or look at the energy sector. These composites are super strong and don't corrode, which makes them perfect for harsh environments like offshore oil and gas platforms. They extend the life of critical equipment and make everything safer.
And in heavy industry, using composite parts reduces the weight of moving components on huge machines. This cuts down on energy use, reduces vibrations, and lets the machinery operate faster and more efficiently than ever before.
So the real story is this. The biggest thing holding back a world built with these revolutionary materials wasn't the material itself. It was our ability to make it perfectly and at scale. Now that AI and robotics have shattered that barrier, it leaves us with one last really exciting question. With their creation now optimized by AI, what limits will these smart composites break next?